Alright, so let's talk transformers. We discussed the basic ideas in class. We demonstrated them as well. So let's put on paper the formal notes that describes it. We'll do a little bit of practice, but most of that will come in class. Alright, so we have two key transformers here. We have Megatron, okay, and you may not realize this, but when transformers were first conceived, when Megatron would transform, it would look like this transformer right here. Okay, the makers of the transformers tested this in the public. I believe this is Japan, and people found that this type of transformer, like this shape, just didn't appeal to people, so they decided, let's make it evil, let's make it a little bit more interesting. But we're still going to go with the simplified version because it's actually helpful from a physics standpoint. So the basic concept, and everything you need to know, is shown in this diagram. We have an input of AC voltage. It's got to be an AC source, not a DC source, because we need a changing voltage, which will produce a changing electric field or a changing current. Okay, we want that connected to multiple turns of wire wrapped around an iron core. Okay, technically it's a ferro really mean iron, magnetic. Okay, any material that would enhance a magnetic field. Okay, and so we have an input on the left. This input in what we call the primary coils is measured two ways. There's two key things we want to know about the inputs. The more obvious thing is the primary voltage, okay, and the second thing are the number of turns, which we'll call N sub P. So we've got a changing voltage in the primary coils, and that creates a changing B field in the core. Okay, and the core just enhances that, just like we saw for electromagnets, which in turn induces a changing, right, voltage or EMF in the secondary coils. That's Faraday's law. Okay, and so the output in the secondary coils is measured two ways, and not surprisingly, it would be our secondary voltage and the number of windings around the second part of the core here. Okay, so what we want to understand is what is our output compared to our input, and it's a very simple transformation. It makes sense, and it's all based on the result of the rate of change of flux being in the primary must equal the rate of change of flux in the secondary. That's really the key to a transformer. If I'm creating a changing flux here, I'm going to propagate through space. It's the same rate of change there. It's just that the output voltage can be different than the input voltage based on the number of turns. So let's see how that works. So we have the primary voltage is equal to the negative rate of change of the flux, which would be negative N of the primary times delta phi all over delta T. Okay? And we know that the secondary voltage is negative NS delta phi over delta T. And as we just said, these two are the same. Okay, they must be the same. There's no reason why they'd be different from one or the other. So if we take a ratio of the two, we look at VP over VN, primary to secondary, VS, we see that it is this whole ratio divided by this whole thing. I'm not going to write it all out. They cancel the fluxes, and we're left with a primary over the secondary. Okay, or put another way, I'm going to invert these. The ratio of the voltage of the secondary to the primary equals the ratio of their turns. And when NP is less than NS, in other words, there's more secondary turns than primary, we have what is called a step-up transformer, and the output voltage is greater. At least than the input. Okay? So we've demonstrated that in class. We saw that with the 200 to 400 turn sets of coils or the 400 to 800. Ideally, if you have double the number of turns, you're going to get double the output of voltage. If you have 10 times the number of turns, you can get 10 times the voltage. And there's really, at least ideally, no limit to that. It's not like you can only go up to 4 or 5 times. In theory, you can go up to 100 times. Let's talk about the iron core. I mentioned that. Now, technically, it's a, if you want to get detailed, it's laminated. I'm not even sure if I'm spelling that right. Laminated, okay, cord. Is to greatly increase the efficiency of the transformation and therefore reduce energy losses. So if you try to just do a primary coils with the secondary coils with no iron core, the amount of transformation is greatly reduced. Okay, so a simple problem. I've got a primary coil consisting of 16 turns. We have a 6-volt AC source. We've got to make sure it's AC. Secondary coil is connected to a 15 ohm resistor and draws 4,800 amps of current. How many turns are in the secondary coil? Okay, so the basic equation we're going to use is the number of turns in the secondary over the number of turns in the primary equals the voltage in the secondary over the voltage in the primary. We just got to do a little work here. Okay, so this becomes the number of in the secondary equals the number in the primary. The voltage in the secondary is just going to be I secondary times R secondary all over the voltage of the primary. Now we can put in numbers. So we have 60 times 50 times 0.48, right, divided by 60, right? I believe 50 times 0.48 is 240. 240 divided by 60 is 4. 4 times 60, they cancel out anyway. So we get 240 turns, okay? So we have a step-up transformer here. Will the input current be also 0.48 amps? We expect the same current on both sides, and the answer is no. All right. Not only does it depend on the resistance on both sides, but it also depends on a more important or more fundamental aspect, and that's power output. So let's turn our attention to that. Okay. Another thing we talked about in class is why don't transformers violate conservation of energy? Okay. We think that if we got a greater, right, if the voltage across the primary is less than the voltage in the secondary, we're getting free energy out of the secondary, we think that's not right. But voltage is not quite the same as energy. Okay, it's an indirect measure. So there are other factors that influence it. Now we're going to see how that comes into play. A better proxy, or a more direct one, would be power. Okay. So what we can say if energy is conserved is the power in the primary must equal the power output of the secondary. That's our starting point for conservation of energy. So let's see how that can be consistent with the idea of stepping up the voltage or even stepping it down. Well, the power in the primary is really just the V of the primary, and it's really an RMS speed, not speed, but a voltage. So I just want to remind us from the previous lesson, times the current in the primary, which again is an RMS because we're dealing with AC, must equal the voltage in the secondary times the current in the secondary. I'm not going to write RMS for both those, but that would also be true. Okay, so we can see very simply that if I take my ratio of secondary to primary, right, which might be stepped up to 5 times the value or 10 times the value, we see that it's equal to the ratio of the primary current to the secondary current. In other words, if Vs over Vp is 5, then the current in the secondary is going to be 1/5. So whatever advantage you get, if you will, from a step-up performance offset by proportional reduction, okay, in current, such that Vi for one must equal Vi for the other. And it's a little bit more complicated than that based on the resistance that you put in there, but that's the general idea. So a really nice thing about this reduction in output current, even though it might seem like a shortcoming, I can only get so much current out of it, which is less than I would be able to input, is it gives us a major advantage in power transmission and power lines. Okay, so like we discussed before, so suppose we need 1 gigawatt of power distributed in the power grid. Well, power lines have a small resistance because of the length, and that length will give us thermal losses equal to I squared times R. And that's important to remember. Okay, that's actually in IB reference tables, the thermal losses, okay? I'm sorry, not I2, but I squared times R. So when we got transmission of tremendous amount of power along power lines, we want to have as little current as possible because it drops off by the amount of energy loss goes by the square of the current. So doubling your current gives you 4 times the power loss. So we want to mitigate these losses, in other words, keep them as low as possible, yet transmit a ton of power. So we do this by minimizing the current in the lines, by maximizing the voltage. And the way to maximize the voltage, in other words, to get it really, really high, is through transformers. Right? That's really the major motivation for teaching this at this level. And transformers work very nicely from AC. So that's why we have AC current or AC voltages, because they can easily be stepped up or stepped down for whatever purpose that we need. And a very, very, probably the most important purpose for society as a whole is to be able to transmit gigajoules or gigawatts of power at high voltages and then be able to step them down to smaller voltages at our home, which aren't as dangerous. So let's say we have a power plant. Well, that dynamo in there is probably generating voltage at around 220 volts. Okay, based on the speed at which is angular velocity and the magnet and all that. We're not going to be producing hundreds of thousands of volts directly. So what we have coming out, we step it up to the power lines to, let's say, 500,000 volts or 500 kilovolts. So that might be traveling for miles and miles and miles and miles at very, very low current. And then when we finally get to near a town, we step it down in the substations. And this is probably, 220, 440, depending on what's going to be tapping into it. And then when we go along the streets to homes, then the convention generally is 220, or, excuse me, take that back. There is some 220, but generally we want 120 in the houses. Okay, so we got transformers to transmit, and when we get to towns, we step it up to go a long distance, and then we step it down for the shorter distances and shorter wires that we would have in our homes. Okay, so the last thing we'll talk about is transformers are not ideal. There are losses in power. The lab that we're investigating is taking a look at that, but we want to know at least some factors that affect it. All right, so why would we get less power output than we input? Well, first of all, our windings aren't perfect. They have resistance. Okay, and the more current we have in them, the more we're going to lose. Okay, so we get thermal losses. On top of that, there are thermal losses due to the heating of the core itself. Okay, when you have that induced or that changing magnetic field, that's going to create up little eddy currents in there, okay, which are going to create some issues, all right? So that's another thing. We have eddy currents, like little vortexes of currents in there, which are creating heat. And this is reduced. The one way you can mitigate this, not have a solid iron core like one material, but like I mentioned before, something that's laminated. Laminated means a bunch of thin pieces that are put together. Lastly, you have a flux leakage. Okay, and what that basically means is not all the flux in the primary is linking to the secondary. Okay, so it takes a good engineering to make sure whatever flux you have is going right to the secondary and not leaking out into the air or whatnot. So those contribute to less than perfect, but I believe transformers, good ones, can be up to 80 or 90% efficient. Okay, we'll do practice in class. If you have any questions on any of this, please come in with those questions.